That's going live. Okay, and let's hit record. Okay, here we go. So thanks everybody for joining the session. We're excited to have Thomas join us to talk about LLaMa 2. So Thomas is a research scientist at Meta AI and is leading the large language models team. He's contributed to LLaMa 2, CodeLlama, Galactica and Toolformer, which are all really cool papers and models. And prior to joining Meta, he did his PhD from Sorbonne University in France. So along with his research activities, he's also an active investor in Gen AI companies, and he supports the growth and development of technologies in this field. So I'm going to pass it over to Thomas to get us started. And I'll also be posting a Slido for you to ask any questions about topics you hear along the talk. So over to you, Thomas.
Yeah, thank you for the introduction and for having me here. So yeah, today I'm going to talk about LLaMa 2 that I guess most of you heard about. But first, I want to start with an introduction about the space of large language model before we had LLaMa 2. So I will start this talk with GPT-3, which was a breakthrough, in my opinion. And well, what they did at the time is just, how can we scale self-supervised pre-training paradigm? So they started from GPT-2, which was, I don't remember, like few billion parameters. And they explored what if we increase the model size, the batch size, the number of steps. And so their results indicated that for optimally compute efficient training, most of the increase that you see the big area, which is in blue, go toward increasing the model size. And so, yeah, scale is all you need. Scale what? Scale the model size, the number of weights of matrix in your model. That was GPT-3. Scale the weights was Ellison, and they went up to, 175 billion parameters. That was like unprecedented by a large margin. And impressively, you can see like with on Trivia QA, a great benchmark and measuring question answering, that just scaling, nothing else, same algorithm, same data, just more compute and more weights to train more compute to train those more weights. You can see that at each scale, you see some improvement that are consistent and follow a log law, where basically you end up with the final model, 175, which gets better results in a few-shot learning, few-shot setup than the state-of-the-art at the time, which was an extraordinary result. And so they show that scaling up the language model is great, and that their model has 10 times more parameters than any previous sparse language, non-sparse language model. And one of the great findings is that this few-shot setting was now what we call the in-context learning, where you can learn or kind of learn an algorithm or a pattern or the behavior you want to do without any gradient updates or fine-tuning, just basically prompting the model. That was the beginning of prompt engineering, maybe. With some examples, example 1, input, output, example 2, input, output. And just with that, you can get the model to follow this template. But the story didn't end it there, and scale the weights is not all you need. So actually, OpenAI did a huge mistake in the analysis, which is that basically they did a single total annealing schedule. And the thing is, with smaller model, you can do like for the same compute more steps. And so the optimizer, the scheduler were not optimal. And because of that, well, the laws they had in the paper were not like totally correct and reflecting the reality. That was emphasized in this great paper by DeepMind, Chinchilla, while they proposed to scale the data as well. So what they said is to train a compute optimal model, they find that the current large language models are significantly undertrained, which means we need more data, more steps. And this is due to a consequence of recent focus on scaling language models, a clear reference to GPT-3, while keeping the amount of data constant. I said that you need to double, for every double of model size, the number of training tokens. What was outstanding in this paper, in my opinion, is that they did all the experiments, ablations, analysis at small scale with models below, I think, 10 million parameters. And so they discovered some empirical laws for which they said, okay, we had trained in the past a model called Gopher with 280 billion parameters. That was a DeepMind model. It used a lot of compute because it's a big model, like almost twice bigger than GPT-3. And yet, from our analysis, we think that the compute was not well distributed, and we should have like trained maybe for a Pareto optimal compute, a smaller model, but with on a lot more of tokens. And so this is what they trained with this chinchilla model. And yeah, they obtained so a model at 70 billion parameters that largely outperformed their Gopher model while using exactly the same amount of compute. So small scale, relatively small experiments to draw some conclusions that enabled to train a larger model. That was a very great result. But then comes the LLaMa paper, LLaMa 1, where I think about it as like rethinking what means compute optimal. Chinchilla was, compute optimal in the sense that you have a compute for your training. You want to get the best results in a table for a research paper. But the thing is, if your model is so good, you want people to use it in daily basis, in practice. And so hopefully, if your model is used and have a huge impact, it will have a lot of inference cost because people will use it and you will infer a lot. And so maybe at one point, your inference cost will even like reach the training cost. That is a success in terms of adaptation by the public. And so training a compute optimal is not only about training and having a good result in a paper. And LLaMa pushed this paradigm to say, okay, models are undertrained. We understand that from Chinchilla. Let's train even like way beyond what means compute optimal for training. And so maybe for the same compute, we could get a better model. But now with a 65 billion parameters or even smaller models, we train them for so long that they get even better and anyone can use them. And so you can see actually in these curves, blue, orange, green, and red, for all the sizes, we train them for 1 billion and 1.4 billion trillion tokens. It keeps decreasing. The perplexity keeps decreasing, and so the loss decreases, and it means that the model continues to improve. So for this model size, you can still improve it by spending more compute. And so it resulted like in a massive so it was also one of the first model open source. Open in the sense that it was gated and non-commercial, but still people could access it. And in very few weeks, the adoption by the public was so huge, people started to put what they call the GPT-3 level AI, because the model is close to GPT-3 level, probably in terms of pre-training, in a laptop, phone, Raspberry, with like 50 tokens per second running locally, calling this like the stable diffusion moment for AI. So that led to a huge exploration in terms of research in a lot of different directions from LLaMa adapters. We had all the name of the animal with vicuna, alpaca, and all the family. So that unlocked a lot of new research. That figure is from the survey of large language model from Wayne Zhao this year. And that was great, but still, it was non-commercial and gated. So people were complaining about like, where's the weights? We want the weights. We want to do products with these weights and sell stuff. And right now we have your model, which is good, but non-commercial, and we have an API from OpenAI. So here come LLaMa 2 that I led recently. So LLaMa 2, we train it on like 40% more data, up to 2 trillion tokens. So we're just extending even more the paradigm of overtraining the models somehow. We increase it slightly, the context length. It's just incremental, we doubled it. But the great thing about context length is that you can do it at fine-tuning, and there's already, as you may know, a lot of works that propose the LLaMa 2 version with a larger context length. And more importantly, I guess, we also released for the first time a fine-tuned aligned with human preference version on more than 1 million of human preference data we collected. So for the pre-training stage, well, it's standard pre-training. We just incrementally increase LLaMa 1 thing with more tokens from more recent data. And yeah, maybe one thing I can say also about an intuition of how good is the next token prediction that we use in decoder-only self-supervised learning. Like there's a question about how understanding and emergence emerge really or not from data. One thing I can give as an intuition to understand what's happening with these models is, but the way I understand it in my head is like, if I give you millions, billions, an infinite number of tokens that I can create for calculus, 2 plus 4 equals 6, 2 plus 2 equals 4, and so on. I can generate like infinite number easily by creating some random data. Then if your task is to predict the next token after the equal, and if you're naive and dumb, maybe you can try to memorize everything, but that will scale pretty badly. And I will even say that with an infinite number of data, it won't generalize to new data. But then if you internalize the algorithm, which is basically compressing information, the best compression in terms of information for calculus, is to internalize the algorithms behind that. And then you can generalize to new data. And this is probably what is happening with those large language models. And that's why the next token prediction is working so well. So we see it's the same pattern with 1.5 more flops than LLaMa 1. The curves keep decreasing. We could have even trained it longer, which might be for future works. And then comes the LLaMa 2 chat, so the supervised fine-tuning aspect. So what you do with a pre-trained model is that you collect some data, like chat-like data, that will follow human preference. And you will do imitation learning, which is just a simple fine-tuning on those data, to align the model first. So we collected data with extraordinary annotators. Here is like think about the task of annotating the data. You need to come with the prompt and the response. This is extremely hard. I tried it myself. Think about it yourself if you are in this situation. After 1 to 5 examples, you don't have any more creativity, at least for me. And so here is an example, a great example from an annotator, like write a poem to help me remember the first 10 elements on the periodic table, giving each element its own line. And then the poem that was also written by this annotator. Those are like gold supervised data. So what you do is that you take the data and you fine-tune the model on that such that it's good enough to move then to what we call RLHF with the human preference. So because you have now a good model enough, you can leverage it in your annotation, which is, I feel, the magic behind RLHF, truly. Like the synergy between machine and human to annotate. So the annotator comes again with the prompt. Can we play a game of hangman? And then we sample 2 outputs from our model. So we have the model that was trained, like the pre-trained model, fine-tuned on the supervised data, the poem you saw before. And then we sample 2 outputs. The model is not good yet, so it won't behave well every time. And so here, well, the first answer is pretty good, but the second answer, like it said, sure, what word would you like to use for the game? I mean, if you want to play hang game, you don't want the model to ask you the game. Otherwise, there's no more game. So arguably, the annotator said, okay, I prefer model A answer. And then based on this data, we can train a reward model and fine-tune with a reinforcement learning on this reward model that is aligned with human preference, our chat model. So a few words about human preference and LLHF. In terms of order of magnitude, it's roughly like $3.5 for a basic comparison. It depends, of course, of what you're asking as a task. Like coding will cost much more, reasoning, math. But then for like just a standard poem, for instance, because you leverage the model outputs, the annotator doesn't have to write the output. It costs an order of magnitude less than if the annotator has to write the poem, for instance. So when I started the project, I was, okay, assuming I have an infinite amount of budget for annotation, maybe I prefer to do only SFT. It's gold standard, it's supervised data. Reinforcement learning is subject to a lot of instabilities. It's a dark area for NLP people. And well, but on the other hand, well, it's cheaper, we need to move fast. So maybe we will do LLHF as soon as possible. Another advantage of LLHF was like, because you leverage the model output, it kind of converges to a consistent mode and not like learn all the distribution and variety of humans. Because if you ask humans to write, like dozens, hundreds of humans annotators to write, they all have their own styles, while with LLHF, the model will converge to its own style. That's another great benefit. But there's actually more important behind that HF. If I ask you this prompt, write a haiku, or like these 3 lines poems in Japanese about large language models. I let you all like 10 seconds to think in your head what you could write there. Think about answering this prompt and writing the answer to this prompt. Well, I'm terrible myself at poems, so don't worry if you didn't find something good to write. But then the model generated something great, actually. And, as a human, I'm not that creative in general. And models learn the good distribution. And so they're able to perform way better in a lot of cases than actually me and some other humans. And so there's a secret behind human preference, which is I found out that the model became much superior to supervised annotations very quickly. And there's a fundamental reason behind that. If I ask, even like think about the best painter in the world or the best writer, maybe sometimes he can write some great books, but some others might be less good. Same for painter, good painting, but sometimes worst quality. Even Picasso will do some painting that he didn't like himself. But then if I ask him, or even someone that is well than him on painting or writing, to judge what books he prefers, what painting he prefers, the task is so much easier. There's way less discussion or polemics between annotators about that. And so you can converge to something which is way beyond the maximum of the annotators. While with supervised fine-tuning, you will converge only to the average of your annotators. You're just imitating the distribution of humans, which can be good if you get good annotators, but everyone does mistakes. So I think we are in a new era now where with human annotation is not the gold standard anymore, at least solely human annotation, I should have said. And yeah, the synergy between model and humans are already scaling way better. So finally, we do this fine-tuning stage. We use 2 algorithms in the paper, standard PPO, but also rejection sampling. So you can think about rejection sampling and being like in breadth, while PPO being in depth, where you update the model each stage. For rejection sampling, maybe a good intuition is, so you have a prompt, you sample 100 outputs from your model, and you score all of them with your reward model, and you take the maximum. And so why that is good? Here we have in this figure like sample from 1, 10 power 0, to 20. And you can see for each number of samples, so assuming we scored all of them with our reward, what would be the median of the reward and the maximum of the reward? Well, if you sample, you can sample an infinite number of times. Beyond the variance, the median should remain the same. It's consistent over time, it's stationary. But the maximum, because the more you sample, the more likely you have to have one sample that is better than the other one, although it ends to plateau, obviously. You are more likely to sample, to have an output that will be scored better than the reward. And so as expected, the blue curves increase over time, over the number of samples, while the median remains the same. And so with rejection sampling, you can basically have a larger and larger and larger gap with more compute and more samples between the median and the max. And then what you do is that you fine-tune your model on supervised data that are actually the model outputs scored the best by the model. And so these give us basically you move the model towards the max of the reward instead of the median, and you progress that way. So what matters, because we select all the samples with the reward model, is the reward model performance. And there's something beautiful about it, which is it's a binary classification task where we have a prompt and two samples, and an annotator said, I prefer this one. And you can just measure that as a classification problem. This is trivial, as opposed to generation tasks, where it's become harder and harder to measure the performance of LLaMa 2 GPT-4 outputs on creative writing, for instance. And so we saw that here on the CSI, you have for every week, we received more data from the annotators, and just scanning the number of data and also the weights, with the red curve being the largest, we get better and better reward models, which enables to apply the recipe and see some improvements on our model. So every week we train new models, or not every week, but mostly. And first with only rejection sampling, and then with rejection sampling plus PPO. And we saw some improvement on here, for instance, on helpfulness, where what we did is we compared a sample from ChatGPT and a sample from our model. And on the left figure, we ask our reward model to judge which one it prefers. So we score the two and we take the max. And you can see that our model gets like close to 80%. But I mean, I will not say that our model is 80% win rate versus ChatGPT, because our reward model is also biased toward our guidance. So what we did is also like asking GPT-4 itself which one it prefers. And more like fairly, I would say, GPT-4 shown that our model is actually better, more than harmless and helpfulness between like 60% and almost 70% of the time with respect to ChatGPT. So here is a good illustration of what I was saying, like with each iteration, you see like the shift from on the curve, where basically you start with a model trained on mixture of data that we collected from academic benchmark, where the reward model judge it like not that well. It's uniformly distributed and a bit too much on the left. Left means bad reward, close to 0, assuming a reward between 0 and 1. Progressively, with some supervised fine-tuning data, well, our annotators are good, so it moves to the right, but still you have a huge tail of bad reward model below 0.5 and below 0.8. And progressively, while we apply RLHF version 1, version 2, and the others, we shifted the distribution to basically flat the left part of the curve. That's what is doing RLHF. That's why, like, basically you're preventing the model to do any mistake as opposed to a human. It's not completed yet, and there's a lot of progress, but that's kind of the process, what it looks like. So maybe I will finish with a few nice examples we found out on the way. So we asked annotators to annotate like just 1,000 of this data. And what we found out is the model generalized to structure its knowledge with a temporal perception. So now if you ask the model basically, okay, there's a system prompt where we tell the model some system-like information, like today date is 1st of January 23, but your knowledge cutoff is the 1st January of 1940. And here's the model, who won the Second World War? The model said, I don't know what you're referring to because my knowledge stopped. So it knows that the Second War happened after, and at with this cutting knowledge, it should not know. And same, like for the Earth flat or round, if you assume you are 2 days, you will talk about like satellite imagery, and so we know that the Earth is not flat but round. But now, if you say that the year is this time 852, well, the model answers something much more related to this time with what the Greeks found at the time, etc. And so, and up to the Renaissance. And we tested this for a dozen of examples. It worked pretty well. So that was interesting to observe. As well as emergence of tool use. Well, yeah, to say in the introduction, also like the last author of Toolformer, that's something that I really enjoy. Toolformer, we did it in a self-supervised manner during pre-training. And what we found out is that with well-aligned model, you can just create a prompt like that, telling the model, you have a search, you have a calculator, that's the way to call them. Answer, and if you need to use the tools to answer, use them. And you can see that when you ask, like, for instance, how many years ago did sharks first appear on Earth compared to trees? Great question, for which, by the way, I thought it was trees before sharks, and it's not. Well, you can see that the model just called search for sharks first appear, then trees, and then use the calculator to do the difference. So I will finish this talk with that. Thank you, everyone, and happy to answer all your questions. We are still building for the next LLaMa, which hopefully will benefit of the community again. Thank you.
Awesome. Thank you, Thomas. So we do have a number of questions coming in the Slido. Let me just try to group those together. So let's start off with this question. So large language models, as you mentioned earlier, GPT-3 was super impressive that it could beat fine-tuned models when it came out. But for other use cases, fine-tuned models might still make sense, smaller fine-tuned models, because they're easier to run and might outperform in other tasks. So the question is, for people fine-tuning their own specialized models, do you have any advice on how to evaluate on open-ended tasks, summarization, copyright, QA, etc.?
Say again?
So the question is, for people fine-tuning their own specialized models, do you have any advice on how to evaluate on open-ended tasks? So summarization, copywriting, QA.
Yeah, I mean, I did half of my thesis on my PhD on evaluating summarization tasks. That's an open research question. There's no great way. I think it really depends on your use cases. For instance, summarization, we developed some metrics based on question answering, like comparing the amount of information present in the summary versus the source document, stuff like that. Then I will even say that now at the state where we are now, maybe you have some special case of summarization where mostly the model is now quite good and factual, but then you want to personalize it. What kind of information do you want to be summarized? How to personalize that? And so we will need to move to new metrics while we progress. So I would say it really depends on your use case, and it needs to be defined according to your product and the KPI you want to maximize.
Got it. Thanks for sharing. On that topic of maybe synthetic data, so it's a question about generating synthetic data where there aren't a lot of instructions. So I know you talked about how generating prompts can be challenging with the answer pairs. Is there a technique that you use for things like translation when you don't necessarily need a complex prompt for synthetic data?
So what about translation? I understand the part about synthetic data, but
for a task like translation, when there isn't a complex prompt, something like translate to French or something, is there any reliable technique that you use?
I mean, in general, so maybe let me answer, and I hope it will be helpful in two parts. So for translation in particular, well, I think there's some very good translation models. So you can collect data, just translating some data there if you want to improve your model. One thing to add is that in terms of multilinguality, models were found to be extremely good. We don't have any numbers in the paper, but I tested myself because I'm French on French, the model. And it's very good, to be honest. And I encourage everyone to test it in different languages. It's not that bad, despite we didn't focus on putting any multilingual data in the pre-training. There's few of them, obviously, but not that much, like no more than a few percent. And that being said, in general, synthetic data, I'm very, very supportive of that. I'm an author of Unnatural Instructions paper. And I use that actually in daily basis for a lot of tasks where you want to bootstrap your performance on new tasks. And so you can create a simple pipeline. You can ask the model to generate instructions if you prompt it properly. Like if you say, I don't know, you have a task where you want to create API calls, you just need to describe it with 1, 2, 3 prompts well-designed and say, okay, now generate me 1,000 examples like that. The model often does pretty well, which helps to bootstrap before maybe annotating, refining later.
Okay, that's great that you're thinking and a big fan of synthetic data, because that's often much easier to get.
Yeah.
And speaking of language, so I was just looking at the LLaMa composition for languages. So it's mainly English data, I think almost 90%. Was there a reason that you didn't put more French or Spanish or other multilingual in the pre-training?
Not specific reasons. I guess it was only LLaMa 2 and we needed to have future work for LLaMa 3.
Keep yourself having a job. That's but
exactly.
It's great to hear that French still worked quite well. That's pretty surprising. Okay, looking through these other questions. So another question, interesting. So there's been the 2 5 papers, the 2 textbooks ones. Do you have any, I guess, comments on them? Do you feel that synthetic data source was well derived? Sort of, do you have any thoughts on that paper or those 2 papers?
No, I think it's a good. I haven't digested myself yet. I don't know what conclusions to hold. How much like there's some distillation from bigger, better models. How much like it really helped or not, and it might be the case. So it's hard for me to say. Yeah, I don't have a clear answer because, see, yeah, actually my answer is we need to investigate more, explore more in this direction to understand better, because there might be something.
Okay, got it. Thank you. And I guess you're talking about maybe some more multilingual functionality in LLaMa 3, but generally when you're training these new models, like obviously when you're doing research, there's hundreds of ideas everybody on the team is coming up with. Sort of for the LLaMa 2 improvements, was that something you thought of while training LLaMa 1 sort of beforehand? How do you figure out what changes you make for the new models?
So yeah, I think LLaMa 2 was, in terms of pre-training, mostly just adding new recent data from pre-training aspects, changing as few as possible, but removing all the data that would make it not compatible with a commercial license. So that was also like more like related to that, so less researchy, I guess. And there was all the new research that we never worked on before, more or less, about alignment and instruction following abilities. So yeah, can you repeat your question for this part?
Yeah. The question was, so when choosing which experiments to run for LLaMa 2 sort of, when did those ideas come up? Was it while working on LLaMa 1 and you said, okay, let's hold off? Or was it after LLaMa 1 came out, everybody sort of did a postmortem and said, okay, what can we improve?
In fact, we started working on LLaMa 2 with the instruction following part before the release of LLaMa 1 as instruction following human preference being the natural continuous of pre-training. And it happened that because of the success and other things that changed, etc., we managed to have support from the leads to also release it in open source, this time properly. And so that came to like the new pre-training.
Okay, great. That makes sense. So speaking of the release, so I know when the model was released, there were a couple of partners. I know Hugging Face and Databricks and Microsoft had hosted versions. So I don't know if you're part of that release process, but what is it like once you have a model that's ready? It passes benchmarks. You have the paper. What happens next after that?
Yeah, that was big. Like there was even Amazon and recently Google joined as a partner. So I feel everyone wanted to partner with LLaMa. I mean, the process was different for every company. Most of them had early access a few days before. Microsoft up to like 2 weeks. They wanted to do a lot of safety checks, responsibility, etc., to make sure like they also like support the release on their side and to test it, which is totally understandable. So I guess there was a lot of pressure to get it basically ready for them, but not ready for us, not changing anything more, or like, maybe last minute changes. When you have a lot of partners, it gets trickier. That's the hardest part, I guess. And then supporting all the different codes, adapting it to the different partners. Yeah.
Got it. That makes a lot of sense. And I guess for running the models, we had a couple questions here on inference. So for running inference, I know during earlier part of the talk, you mentioned that it might end up being more expensive than the training portion. So do you have any recommendations on running inference? Anything that you've seen sort of since the paper was released that works well?
Yeah, so I'm not familiar with all the inference, that's not my expertise, but so all the quantization, towards 4-bit Stera, the CPP from Karpathy, also speculative decoding seems to work quite well when you are not like compute bound. I feel like all those areas are somehow sometimes orthogonal, and there's a lot of improvement that can be made. Maybe in the future we can also release some inference code as well. We are working on that.
Okay, got it. And sorry, jumping back to training data. So there was not a lot of code released. Obviously, CodeLlama came afterwards. Was that because those were two separate work streams, or was there a reason to omit code, even though it showed that it improves some logical capabilities of these kinds of models?
Yeah, I mean, we did put a bit more of code, but in particular for the alignment fine-tuning, we did not focus at all on code, while the CodeLlama team did. So we partnered with them for CodeLlama, and hopefully we keep working on with them more closely for the next releases.
Okay, got it. Yeah. So a couple more questions here for some of the retrieval augmented generation and maybe tying it back to prompting too. So there's a paper preprint that came out about sort of autonomously changing prompts using a generator model and an evaluator model that DeepMind released. So for when you're training the prompts, did you have any kind of inversions or ablations? I know that's something that the Flan paper also talked about putting the question first and the answer or the context. Was that something that was involved in the pre-training process, or did you have sort of a consistent format?
What do you mean exactly?
So for example, when you have your prompt and then your generated answer, sometimes for questions and answers, you can put them in reverse order or have additional context in there. So was any of that sort of taken into consideration?
I see.
There. Not
really. Not saying we should not, but we didn't.
Okay, got it. Okay, that makes sense. So, okay. For everybody in the audience, if you missed it, there are questions in Slido. So if you have any questions, I'm just going off of those to respond to those ones. Okay, we have a couple more minutes. So for annotations as well, there's a question about validating the quality of human annotations. How did you do that? Because I know sometimes data labeling is messy. Did you use any techniques of using subsets or sampling? Sort of how did you know that what the humans were providing is good?
In fact, I would argue that human preference on 2 model samples is way less like difficult to evaluate and to do actually in practice than writing yourself. So that's less a problem somehow. Doesn't mean like you don't want to measure diversity of the prompts written by annotators, data constants. We also use like some companies that provide those kind of services where they do some QA themselves to maintain the performance, etc. And then internally, we did also some reviews with each batch to check a few examples randomly, see what it gets, does it follow our guidelines, etc.
Got it. And I guess for prompting, do you have any recommendations for prompting LLaMa, whether it's generating specific formats or formatting the output like in JSON or other machine readable formats?
Yeah, I think one underused feature from LLaMa 2 right now is actually the system prompt, where you can like ask it or answer always with one sentence, answer with emojis, answer with a JSON format, start always with hello. And it kind of works pretty well for some turns. So that can help in some situations.
Okay. So for the system prompt, I guess I know ChatGPT 3.5 had a much weaker prompt than GPT-4. Did you benchmark where LLaMa 2 falls on that?
I have an intuition that we are close or on par with GPT 3.5. We seems to be better on some aspects, clearly worse on some others, in particular, like for instance, code. Mm-hmm. So I would say more like close to GPT 3.5 level than GPT-4, clearly. Mm-hmm. But we're working on that.
Okay, for sure. Okay. I guess another question here on the actual collaboration aspect. So there's a lot of people on that paper. How do you work with so many people on this kind of project? Is it by area or how does that work?
Yeah, there's some people that naturally focus more on alignment, fine-tuning, some on pre-training, some on data pre-training, some on annotation, some on, evaluation. And yeah, that was a challenge to get everyone aligned with the prune, but yeah, I guess it did not that bad.
Yeah. Okay, now going into the model itself, there's a question about safety violations between the different variations. So 13 billion and the 70 billion parameter model seem to have lower safety violations than the 30 billion one. Is there any intuition behind that, or is it a coincidence and some kind of convergence?
Intuition behind the fact that what exactly?
Why the 30 billion model has more like safety violations compared to?
Yeah. For the 30 billion. I don't know. And we didn't get the time to check in detail, which is why we decided to not release it as simple as that. It could be just a simple bug, or like, when we run the model, forget some data sets of safety. And because of that, we chose to not just release it for now. And we didn't have the time to work on that.
Okay, got it. Then another question about the context length and maybe some of the positional embeddings. I guess you increased the context length, you doubled it. Was there a reason why you didn't further increase it? Because that seems to be a trend. Let's make it 16,000 or 100,000 or 32,000.
I don't know, because most of the paper that does that, or the model, not the paper, in fact, that do increase the context length are like end model behind an API. And I'm not sure it's something it's still unclear and under investigation, but how much you should do that at pre-training or at fine-tuning. And I tend to feel that, and there's like in CodeLlama, for instance, we did that fine-tuning only, and we did show that it works very well. You don't need like to move to 32 and even like 100,000 without any problem at fine-tuning. So I guess the message was more like, we don't want to release like the perfect model with like all the features that the competition has, etc. Something everyone can do. Better to release it 1 or 2 months before, and everyone can already start working on that, and we can parallelize with the open source community and work together on that, than wait 6 additional months and do all the little tricks that the competition does, but never see the model out.
Okay, got it.
And that's the same answer actually for code, you know. We didn't get the time to do everything. No code, no long context length. We're working on that, and probably we will release the better model, hopefully.
Yeah, for sure. Always ways to improve. And I guess a couple of questions on the reward model or preference. So when you were, I know there's been some papers about sort of stylistic preference of models versus actual factuality, sort of when evaluating head-to-head. Was that something that you ran into when trying to evaluate things, or was there like a truthfulness score that was still that was still achieved at a pretty high level?
Related to factual consistency in particular,
yes.
You mean?
Yes.
Well, we annotated some examples for factual consistency, not enough, probably. We started to do it more at the end. We waited for the model to be more aligned, actually. I don't know, I'm torn about this because I feel our model is not good for some examples. There are, for instance, this blog post recently that measured factual consistency and summarization. And they showed that LLaMa 2 was on par almost with GPT-4, way better than GPT 3.5. So because factual consistency is like very broad and difficult to measure, I don't have like better answer than that. I don't know, and probably for some aspects we're not that bad. Some others we should progress.
Gotcha. And then a question about using LLaMA chat versus the pre-trained model. Are there any recommendations for tasks where they outperform one another?
I mean, the chat version also has a bit of personality that we injected in automata, etc. So if you have a task where you require to modify that, probably hard to work from the chat model mentioned. The pre-train will be a better fit. Otherwise, it's hard to say. It really depends on your task. So we say test. Test both, as always in machine learning.
Oh, okay, great. And maybe one last question, stepping outside the bounds of the paper and research, maybe you can elaborate a little bit more about your experience in academia and industry, sort of why you went into a PhD and sort of what your general experience was for that.
Sure. I mean, what happened is that I started in finance. I was a commodity derivatives trader in France for a few years after engineering school. And I discovered a tool called AI, and it seems like a science fiction to me. I always love science fiction. And so what I did is that I pursued an executive degree about AI, which at the end of which I knew nothing, basically. I knew SVM, but I didn't know anything about deep learning. That was the year AlphaGo went out. And it felt so magic that I wanted to explore more in depth what it is. Most of the people at the executive degree were doctors, and including the professors, but also students that did this like training after like a few years, dozens of years, setting some companies, etc. So I wanted to understand more. I wanted to do a PhD. So I did a PhD in AI. And well, lucky for me, I ended in language, which I think I'm lucky because it was not like a guess or prediction that it will be the big thing. And yeah, it did well.
Yeah, I mean, have a number of very good projects under your belt and probably many more coming up. So, okay, I think we'll wrap it up here. Thank you so much, Thomas, for joining us and going through the paper and some important items. Would you be willing to share the slides for this talk?
Sure, absolutely. And thanks for having me.
Yeah, thank you for joining. Thank you, everybody, for joining the call and asking your questions. Some really great questions out there. And yeah, hopefully we'll at some point see LLaMa 3 and get to chat more about that too. So.
Maybe, yes.
All right. Thanks, everyone.
Bye.